Hi friends. So the FIR filters and the IIR filters, once designed using some mathematical equations, need to be actually implemented in hardware. To develop the system of an FIR or an IIR system, of an FIR and IIR filters, we need to actually understand which type of components or elements we are going to use to actually realize this filter. So the next module which we are going to understand or study is the realization of the FIR or the digital filters. So we are going to understand or study the realization of digital filters. So how to realize or how to actually understand or implement a digital filter. So basically we have two types of filters, so we will have two types of realization techniques. One is called as IIR realization technique and one is called as FIR realization technique. So we have impulse invariance method infinite impulse response filter design realization, and we have FIR or finite impulse response realization filters of filters. So there are basic methods to design IIR filters and there are basic methods to realize FIR filters. For today, let us understand what is or what are the types of realization in IIR. So the IIR, that is infinite impulse response filter, is realized using three basic methods. One we called as direct form method or direct form structure. Second type of realization is a cascade realization. Okay, we called it as cascade form of structures. And lastly, we have parallel form of structures. So we have direct form structures, cascade form structures and parallel form structures of IIR filters. So in basic, we will have three types of realization in IIR filter. Let us see what I mean by realization and how actually we are going to implement that equations into reality. So let's say that the transfer function h of z is a set of zeros to set of poles, right? So I have a numerator polynomial which gives me set of zeros and I have a denominator polynomial which gives me a set of poles. So I can represent that polynomial in a different fashion. So that fashion is like this. You can write h of z as summation k is equal to 0 to, let's say, m b of k z raised to minus k. So this is the numerator polynomial representation, whereas denominator I can write as 1 plus summation k equals to 1 to, let's say, n, okay, ak z raised to minus k. Okay, so this is my numerator, this is my denominator. For example, you can say that we can write like this. Let's say we are writing in terms of negative indexes of z. So let's say z raised to 0 plus 1 z raised to minus 1 plus 4 z raised to minus 2 divided by, here I can write it as 1 plus, okay, let's say 2 z inverse plus 3 z raised to minus 2, just random numbers to give you realization that how actually this summation stand for. Now here if I put the value of k, you see k is equal to 0 in this case, here in this case k is equal to 1, and here in this case k is equal to 2. So maximum value is 2. So k is going from 0 to 2. Whereas here I have 1, then here k is equal to 1 and here k is equal to 2. So here n is also equal to 2. So now here in this case our m is equal to 2 and n is also equal to 2. Okay. So if m is equal to 2, n is equal to 2, this is a numerator polynomial, this is a denominator polynomial. And if I solve this numerator and denominator polynomial, I am going to get 2 sets of zeros from the numerator and 2 sets of poles from the denominator, 2 sets of zeros from the numerator. So this is one method of just representing the h of z. But it's very important. What we see is, we have 2 polynomials which we need to implement. One we called as h1 of z, and second let us call it as h2 of z. So this I called as h1 of z, and 1 upon this term I called it as h2 of z. So now let us write it down, h1 of z and h2 of z. So I have h1 of z is equal to summation k is equal to 0 to m, okay, b of k z raised to minus k, and h2 of z is equal to 1 upon 1 plus summation k is equal to 1 to n a k z raised to minus k. Okay, and I can write h of z as h1 of z into h2 of z. Right? So this is what we can do. Now let us see that how we can individually visualize h1 of z and h2 of z. So how we can just draw a simple structure. If I wanted to draw a simple structure of this equation, then I can write that if I give input as x of n, and if I get the output as y of n, then in between I have 2 systems. One is h1 of z, second is h2 of z. In all, this system is h of z. Right. So now I have a system h of z to which I give input as x of n, I get the output as y of n, and then that h of z is comprised of 2 systems, h1 of z and h2 of z. As we see that h1 of z has all the zeros into it and h2 of z has all the poles into it. So it's an all zero system, this is an all pole system. Okay, let us realize. So what I can say is, if I wanted to now elaborate more on the numerator part, what I say is, for h1 of z, my input coming, let's say, is x of z and my output is something w of z. You can also write in terms of x of z and y of z. So like for example, I write this as x of z and this will be my y of z, and intermediate node is, let's say, w of z. Okay, so the output, the x of z and w of z is the output and x of z is the input to h1 of z, and y of z is the output of h2 of z, whereas w of z is the input. Okay, so let's see the first system. Now h1 of z, which is nothing but w of z by x of z, is equal to summation k is going from 0 to m. Okay, then we have bk z raised to minus k. Correct? Now if I open this up, it will be w of z by x of z equals to let's say b0 plus b1 z raised to minus 1 plus so on so forth. I go bm z raised to minus m. I am just putting the value of k from 0 to m. Okay. Now multiplying by x of z to RHS and LHS, you get w of z equals to b naught into x of z plus b1 z inverse x of z plus dot 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 plus bm z raised to minus m x of z. Right. Now let us take inverse z transform. Now let us take inverse z transform and let's say that this is my output y1 of n. Okay. So w of z inverse z transform is y1 of n, that is the output of system 1. b naught will be as it is and then x of z will be x of n plus b1 as it is. Now z raised to minus 1 is multiplied by x of z, then this will becomes x of n minus 1 plus we go all dots till b of m x of n minus m. Okay, so this is the z transform of inverse z transform of this. This is inverse z transform. This is also inverse z transform of this. Okay, now you see that there are some multiplication of some factors. We have x of n which is delayed by one factor which gives x of n minus 1, which is delayed by m factor which will give x of n minus 1. So we wanted to delay x of n, we wanted to multiply that, and we also wanted to add to get the final output. So how we can realize it? So for delaying, we know that there is one digital device which we called as D flip-flop, but here instead of calling it as a D flip-flop, I will call this device as a delay block. So the delay block is denoted as Z inverse. So this is called as a delay block. Okay, then we have to let's say add the numbers. So we want a adder. So this we have an adder which have, let's say, signal 1 and signal 2. So the output will be 1 plus 2. Okay, here if you give the input as x of n, this block will provide the factor of 1 point delay which is x of n minus 1. So this is called as delay block, this is called as the adder block or sum block, and then we wanted to multiply. For multiply there are two basic methods. One is you can show a op-amp structure on a line. If you give x of n input over here, and if on the op-amp, if you on the amplifier you show 3, then it will be 3x of n at the output. Or you can always make a simple line on which you put an arrow, and on arrow you put 3. If I give x of n, then this will be again 3x of n. Okay, so these are the multipliers. Okay, this one and this one also. So these two are the multipliers. So we have basically 3 blocks, because we have seen that in the transfer function I required 3 blocks to realize the output. One is a delay, that is this, then addition which is done by this device, and which is a simple adder, and these are the amplifiers. So now we are ready to jot down or create a logical circuit diagram of a given transfer function. Now if I wanted to make a logical block diagram of a function which is y1 of n which is equal to b naught x of n plus b1 x of n minus 1 plus dot 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 plus bm x of n minus m. If I wanted to make a block diagram of this, then I know that I want a x of n signal first, okay, then that x of n signal is going to be delayed by a factor of -1, okay, and the output here after delaying will be x of n minus 1. Then I will delay it further, and this will be z raised to -1, and here the output will be x of n minus 2, and so on and so forth till the last delay block, which is mth time I will delay, and this gives me a delay of x of n minus m, which will go like this. Okay, now you got the outputs. Now you have to multiply. X of m minus n is multiplied by b of m, right? This is multiplied by b of 1. This is multiplied by, this is multiplied by b of 2, and this will be multiplied by b of 1, and then this will be multiplied by b of 0, because here x of n is going like this. Now we have multiplied. After multiplication, the factors that I am going to get at this line will be b naught into x of n. Then here I am going to get b1 x of n minus 1. Here I am going to get b2 x of n minus 2, and here I am going to get bm x of n minus m, right? Now once you got these factors, you have to add them. To add them, we need to put a adder. So let us put a adder. So I put a plus sign. Remember, an adder will have only two inputs and one output. So I will add adders to it. And then finally I get the output as y1 of n. So now this is how we are going to realize a filter. So this is just the half structure. Okay, what we have received? We have received z inverses, which are multiplied by b0, b1, b2, bm, and then we are going to get a y1 of n. This is h of z, h1 of z. Similarly, if you see h2 of z, then it will be h2 of z will be equal to 1 upon 1 plus summation k goes from 0 to n, right, ak z raised to minus k. Okay, now again it will be output upon input. So now my output is y of z, but the input to the system is w of z, okay, which is equal to 1 upon, okay, 1 plus summation k is equal to 0 to n ak z raised to minus k, right. Now you need to multiply here, cross multiply. You are going to get 1 plus summation k is equal to 0 to n ak z raised to minus k, the whole multiplied by y of z equals to w of z, right. Now if I multiply y of z inside, I am going to get y of z plus y of z into summation k is equal to 0 to n ak z raised to minus k, which is equal to w of z, right. So now once we have received this w of z, I can write the final y of z as y of z equals to w of z minus, okay, let's say y of z into summation, okay, k is equal to 0 to n. Now I'll put it in a bracket because we have minus sign outside, ak z raised to minus k. Right? Now, if you open this bracket, multiplying yz inside will give me w of z minus, okay, w of z minus, this will be y of z into a0 plus y of z into z raised to minus 1 a1, right, plus dot 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 plus y of z into an z raised to minus n, correct. So that is what my equation will be. Now let us break the negative side inside and flip a little bit. So you get minus y of z a0 minus y of z z inverse a1 plus dot 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 plus minus, it will not be plus, it will be minus now, minus y of z an z raised to minus n, and I write here plus w of z, just flipping the terms. Now we got the negative terms, okay, and with 1. If I take, now this is yz equals to, right. Now let us take inverse z transform. Inverse z transform of this will be y of n equals to minus, this will be y of n into coefficient is a0 minus, I will write the coefficient ahead now, a1. Now this is z inverse y of z will give me y of n minus 1 minus so on and so forth minus, I write an y of n minus n plus w of n. And what is w of n? It is y1 of n, which is the output of the previous stage. Okay. So now let us realize this. Now what we find is, let's say we have minus a naught minus a1, because we have only adder, we don't have subtractor. So we have minus a1 coefficient, minus a0 coefficient, minus an coefficients we have. And then I can replace, again I can write it like this, y of n equals to, okay, yn into minus a naught plus minus a1 into y of a minus y minus 1 minus plus so on plus minus an y of n minus n plus w of n. Agreed? So now what I will do is, I will take this output and I will realize the structure. So how the structure will look like? Y of n itself, okay, depends on y of n with the coefficient minus a naught, okay, which is in general 1. Then you have y of n minus 1, which is delayed of a1, and so on and so forth. So let us draw this. So I will get input as w of n and I have output which is y of n. But y of n output, that is this one, is addition of, okay, let's say w of n, it's addition of w of n which is coming straight with no coefficient, added by the delayed function of y of n. So I have this added. Now I need to delay this first. So I'll delay it. I'll delay it and I'll give it to a delaying block, and this I'll get one delay. This is two delays, and this is the nth delay. So what I have now? I have this function. Here I have y of n minus 1. Here I have y of n minus 2. And here I have y of n minus n. Right. So now I will multiply. Here with n1 I have minus a1. Here I have minus a2. And here I have minus an. Okay, then I need to add them. So let us add them. So I will put a adder over here, which will go in this place. Then I will have an adder over here, which will add up to this point, and I will have adder over here also, which will add up to this place. Understood? So this, we see that it is going behind. Previous structure was coming ahead and this structure is going behind. Okay, so now we see that the total y of n will be w of n coming from here with coefficient 1 and then delayed version of y1. So what will be value coming over here? Input is minus a1 y of n minus 1, and here will be minus a2 y of n minus 2, and here it will be minus a n y of n minus n. Okay, so if I see combinedly these two structures, okay, then I am going to get h of z. So let us quickly draw the combined structure. So for the combined structure, I will have x of n as the input and I will have y of n as my output, and in between somewhere I am going to get this will be my w of n. So this will get delayed z inverse, this will be z inverse, and so on so forth. This will be z inverse. Oh, here also z inverse, z inverse, so on so forth. Here also z inverse. Let's say this is the mth z inverse and this is the nth z inverse. Okay, then I'm going to get adder over here, adder over here, and an adder over here. I'm going to get an adder over here, then an adder over here, and an adder over here. Right. So this is h2 of z, this is h1 of z, combinedly this is h of z. Okay. So here I am going to get b1, b2, bm. Here I am going to get minus a1, minus a2, minus an. Okay, and you are going to get here as b0. So this is the structure of an IIR filter, which has backward direction also and forward direction also. Backward direction denotes the poles, forward direction denotes the zeros. So in an IIR filter, we normally have a pole zero structure. So we will have a forward going direction also and reverse going direction also. The pole coefficient has to be negated in the structure as it has been seen, but 0, there is no need for negation. 0 will move from x of n to y of n direction. Poles will move from y of n to x of n direction. That will be reverse direction. So poles are feedback structures, zeros are feed forward structures. This is what the complete structure, which we called as IIR direct form structure, which has been directly taken from the transfer function. So this is a direct form of IIR structure. This is how we realize a direct form IIR structure, which is the simplest one. So this is just a simple direct form IIR structure, which has been directly implemented looking at the transfer function. So I hope that you understood that how actually we construct a logical diagram from a transfer function to give a brief or to give an understanding that how the circuit will look like. Thank you.